So we went through the chapter on conservation of energy. And energy was an important concept because it was conserved. And if something is conserved, then it's a bookkeeping tool, meaning you know how much you have at the beginning, you know how much you have at the end, and you can account for that. So the concept of linear momentum is the same idea. We're going to see that under some circumstances, the quantity of linear momentum is conserved. Okay, now linear just means it's moving in a straight line. So for this chapter, we're going to have objects moving in a straight line, okay, like the baseball here. Later on, we'll look at something called angular momentum, where maybe we have a rotating wheel or a disc, or we'll look at a figure skater spinning around. We'll talk about their angular or rotational momentum. Okay, so this chapter looks at the concept of linear momentum. All right, so Newton had the concept of momentum, and we actually use the little letter P. Okay, now we use capital P for power, little p is for momentum. And I'm not going to keep saying the word linear momentum. I'm just talking about, I'll just use the word momentum. Later on, we start doing rotational momentum, then I'll have to point at that and call it angular momentum. For now, we're just calling this momentum. All right, and historically, they think eventually people started using the letter little p because Newton, about 3 centuries ago or so, talked about an impetus of a force that caused something to move or speed up. So that's where they think the P came from the word impetus, for the force giving something some type of motion. So Newton thought of linear momentum as a measure of a body's quantity of motion. Okay, now that sounds kind of a vague topic, like how much motion does something have? So it's kind of a composite idea. So in this class, everything has mass. Okay, next semester you'll deal with light. Okay, but in this class, everything has mass. Especially in this class, everything is handheld or bigger. So if something has everything has mass in this class, and if something's moving, then it has momentum. So the linear momentum is defined as an object's mass times its velocity. And the units are kind of strange. This has units of mass times units of velocity. So don't get that confused with a Newton, because a Newton is a kilogram meter per second squared. That's a totally different unit. Okay, don't worry about that. Okay, so the units of momentum are kilogram meter per second. It's not grouped together and named after anyone else. Okay, so it's a kind of a composite idea. All right, so for example, let's say here I have a big truck that's moving, and here I have a little bug. That's a bug. Okay, a bug that's moving. Could a big truck and a little bug ever have the same momentum? Okay, well, yeah, because the truck has a huge mass m, but maybe the speed of the truck is small. Okay, the bug has a small mass little m, but it would have to have a large speed. So these two quantities could actually be equal. Okay, so it's a composite idea of mass times velocity. Okay, so in this picture here, okay, so the baseball is moving to the right, so the velocity points to the right, and this is a vector equation. Okay, so that says the vector on the right has to equal the vector on the left. So if the velocity is pointed to the right, okay, if I multiply it by the mass, that doesn't change the direction. So the momentum points in the same direction as the velocity. So this arrow is the velocity, that arrow is also in the same direction as the momentum. Okay, so we have this new quantity momentum. How do we use it? All right. So we want to know, how is this new stuff related to the old stuff? All right. So in the old chapter, we'd say you have a mass, you apply a force, the object accelerates. Okay, so that was Newton's second law, net force equals ma. So I'm going to write acceleration as change in velocity with respect to time. All right, and we're doing objects that have constant mass. So if the mass is constant, I can move it inside here. Okay, so the mass moved inside here. So the mass doesn't change, so I can move it in or out of that delta. Okay, so this quantity here, mass times velocity, is what we're going to call the linear momentum. So I went from Newton's second law, F equals ma. I wrote acceleration as change in velocity over time. I brought in the m right there, and then this quantity is our new idea of linear momentum. So this is also Newton's second law. So if you ask someone on campus, what's Newton's second law? They could give you F equal ma from an earlier chapter, or they could tell you that the net force is the time rate of change of the momentum. Okay, so again, previously you applied a force to something with your finger, okay, and we would say the object accelerated. Now in this chapter, we'd say you apply a force and the object's momentum change. Okay, it's motion change, and we talk about that motion in terms of its linear momentum. Okay, all right, so there'll be some verbiage in the chapter. So one example is, let's say you have a system, and I'll show you some videos in a second. So here I have some carts sitting on a track, right? So the book might say, let's say you have an isolated system, okay? So a system is said to be isolated if there's no net external forces on it. Now, obviously you have mg, you have normal force, but those cancel each other out. So the net force on this car is 0, okay? So if there's no net external forces, the system is said to be isolated. So I don't have any fingers coming in to push, okay? So these two things sit here. They both have a normal force on them. They both have the weight, okay? They're not accelerating. There's no net external forces. System's isolated, okay? Now, another term you'll hear is the system is closed. So that's why some books put a little dotted line or a little wavy line around these two objects to say they're the system. So the system being closed means that no other bodies enter or leave the system. There's no other mass, number 3, that's going to come in here and hit any of those. So here I have a closed and isolated system. There's no external forces, or there's no net external forces, and there's no third mass that comes in. So if that's the case, okay, if I have a closed and isolated system, which most of these problems, as long as we identify which objects we're talking about, that'll be the case, and we'll see that in our lab we'll do soon. So if I write down Newton's second law for momentum, if the net force is 0, the external force is 0, that's 0, okay? So then what I can do is I can multiply, I'll just write over here. So I have 0 equals change in momentum over change in time, and then I can multiply both sides by delta t. And then left side is still 0. Those cancel on the right side. So that says that if there's no net external forces, okay, on the system, that means the momentum can't change. And if the momentum can't change, that means the momentum's constant. And if something's constant, that means the initial momentum of the system has to equal the final momentum of the system. So that's our law of conservation of linear momentum. So now you can identify when this concept of momentum is conserved. So we'll see, we'll have two carts up here like this. We can do a collision. And as long as we only have the two carts, there's no other third cart that comes in, no other finger that comes in and pushes, we'll see that this concept of momentum can be conserved. It's a bookkeeping tool. All right, so this is another way of looking at Newton's first law. Okay, remember Newton's first law, body at rest remains at rest, body moving at constant speed, continue to do so. Okay, we could have said a body with 0 momentum, meaning it's not moving. Okay, remember momentum is mv. If it's not moving, velocity would be 0, momentum would be 0. We could have said a body with 0 momentum continues to have 0 momentum unless some force comes by and changes it. That could have been Newton's first law. Or a body moving at straight, or a body moving with constant momentum, meaning constant velocity, will continue to have constant momentum until acted upon by a net external force. So it's another way of looking at Newton's first law. Okay, so I'm going to show you a video of something I have here. So I have two objects, okay, I have a spring attached, and I inserted a spring. I squish these things together by pushing my hand, so I compress the spring, okay, and to keep the objects from springing apart, I tied a rope. That's a rope, okay. So these two things are held together by the rope. If the rope wasn't there, these things would spring apart to the left and the right. And here I have a little flame. That's a little candle. Okay, and when the candle burns the rope, these two things are going to break apart like the picture down here. Okay, so remember momentum is mv. So here I ask, what's the initial momentum of the system? Well, system's not moving, so initial momentum is 0. Okay, after the string breaks, okay, so candle burns the string, these things break apart, all right. I want to figure out, well, what happens to the system now? What happens to the momentum? Well, where these two things break apart, if this is my system, that force, this number, the spring pushes on number 1, spring here pushes on number 2. Those are internal forces to my system. Okay, so there's no external forces. There's no fingers that come by. So those forces are internal to my system, so there's no net external forces, so momentum's conserved. So initial momentum is 0, that means the final momentum has to be 0. Okay, so I wrote my final momentum as P1 final plus P2 final, okay, because there's two objects, so the final momentum 0. And so I brought this one over, and that says that the initial, that P1 final is equal to minus P2 final. So the final momentums are equal and opposite. So for example, if this momentum is 3, okay, if number 2 has a momentum of 3, and I'm making that positive because it points to the right, then momentum of number 1 would be minus 3, okay, with the correct unit. So they're equal and opposite. Okay. Here I put in P1 final is M1 V1 final, and P2 final is the vectors M2 V2 final. All right. So I wrote this over here. Okay. So I'm using a special case because in the video I'm going to show these two masses. These two objects have the same mass. So for M1 and M2, I just wrote it as M and M. Okay. So the masses drop out. Okay. So that says that they go away with equal and opposite velocities. So if number 2 goes off at 5 miles per hour, okay, then number 1, that says number 1, goes off at minus 5 miles per hour. They break apart with equal and opposite velocities. Okay. Now remember, speed is the magnitude of the velocity. Remember, speed is the magnitude of the velocity. Okay. So if I take the absolute value of both sides, that says they break apart with the same speed. Okay. So one way I can demonstrate that, okay, how do I know that they would break apart the same speed, is what I'll show is I'll put them in the middle of the track. Okay, so they start, let's say, at the middle of the track. Okay, and then I press a button. So in the video I show each of the carts have little springs. I hit a button, spring breaks them apart. And if they're in the middle of the track, and if indeed that they break apart at the same speed, you're going to see in the video that they hit the end of the track at the same time. So that shows indeed that they do break apart with the same speed.